All right, so today we're going to talk about vectors. It's our new topic. It's chapter 8. Remember, you should have your note sheet that I gave you. We'll try to go through the basics. You'll get better at this. I'll get better at this. But you'd like to kind of follow along, use the notes, and get as much out of it as you can. If you miss something that you think is important, go back and watch it again or stop it and pause it. I've included a few examples that I worked out. You'll want to try to make use of those as well. So we're going to start with the vector. Now, vector is a word you've probably heard before. Some of us don't even know what it means. A vector is very simply something that represents a magnitude and a direction. So what is a vector? It's a geometric representation of something that has a magnitude, which is how big or how much we're talking about, and a direction. If I tell you that the wind is blowing at 10 miles per hour in a direction that is north, that's a vector. That vector would look like this. Usually we draw north up, and we'd say this is a 10 mile per hour vector. If I told you that your airplane was flying to the east at 200 miles an hour, and then there was a wind vector that was blowing south, maybe at 4 miles per hour, that's kind of the situation that would look like. So this is your airplane flying to the east at 200 miles per hour. This is your wind blowing south at 4 miles an hour. To be honest with you, it doesn't matter where you put this one. You could put it there. But the most important thing is that, well, if you think about it, if you have a vector going this way and a little one going this way, your plane is probably not going to actually fly due east. It's probably going to go a little bit south of east because of this wind. And it turns out that this little triangle, the hypotenuse of that triangle, would actually be the vector that we're looking for. I'm getting a little ahead of myself, but that's what a vector is. If you take a quick peek at number 1 on your first worksheet that I gave you, they asked you to identify the magnitude and the direction of this vector, and they call it vector x. And they usually draw a little arrow over it. So an x or whatever variable with a little arrow is the notation for vector. And I'm not expecting you to go home with a ruler and a protractor, so let's just estimate some of these and to say, okay, this particular thing, if you look at your paper, it looks to be about 3 centimeters. So we'd say that the magnitude equals about 3 centimeters, centimeters, and the angle, which would be the direction, so we could say direction, and you could approximate it. You go, it kind of looks about 75 degrees, or maybe you thought it was 80 degrees or 70, but it's about 75 degrees, and that would be above the horizontal. All right? If this is vector x, and I'm going to erase some of the stuff to give me some room here, but if this is vector x, which vector x represents a specific magnitude and direction, what do you think the opposite of vector x would look like? Well, if it's the opposite of vector x, the magnitude hasn't changed, but the direction certainly has. So if I wanted to draw vector x, it's probably going to look about the same distance, but in the opposite direction. I mean, if you wanted to tag it right on here, you could, and say that's negative vector x, but in the opposite direction. So if we said this was 75, this would have to be 75 plus 90 degrees down there, and you could go from there. If you wanted to, if you took a peek at number 5, I'll show you how to do that here in a second. If you take a peek at number 1 again, I know I already explained it, but you'd be looking for the length and the approximate direction. Length's about 3 centimeters, direction's about 70, 75, at 80 degrees. That'll work. If you look at number 5, 5 specifically is a subtraction problem, vector x minus vector z. If you sketch them out, and remember the opposite of z would go in the opposite direction of vector z, you'd be looking for the diagonal of that. All right, we're back. If we're going to talk about adding two vectors together, the result, and it's no coincidence, is called the resultant vector. So if you have two vectors, you add them together to get one vector, that would be what we call the resultant vector. Situations like this, if you had a freshman and somebody pulled the freshman this way and somebody pulled the freshman this way, these are two vectors. the freshman is probably going to move in this direction. This would be the resultant vector. This is the actual result of these two things put together. There's easy ways to do this, and that's if the directions are if the vectors are in the same direction. So let's say we had vector A, and vector A maybe is a 4 Newton force. You might not know what a Newton is, but just for right now, just know that it's a force. And then there's another vector that's this way. We'll call it vector B, and I've drawn it a little shorter, so we'll call it 3 newtons. Overall, they're going together in the same direction, so that we would say that our vector A plus vector B would equal a 7 Newton force to the right. And you could draw it as an arrow as a 7 Newton force to the right. Okay. What if they're going in opposite directions? So we have a particle that's getting pulled this way with some, we'll use a different, we'll use pounds now. So maybe we have a 5-pound force to the left, and then we have an itsy bitsy teeny little 1-pound force to the right. Overall, they're canceling each other out, or not entirely canceling each other out.
Mr. Ellsbury, please call extension 273. Mr. Ellsbury, please call extension 273.
5 to the left, 1 to the right. The overall vector of this would be a 4-pound force to the left. What if they're at right angles to each other? As you might guess, we're going to use the Pythagorean theorem. If we have a wind blowing due north at 5 kilometers an hour, and then we have some little crosswind, maybe at 2 kilometers an hour, and we wanted to find the resultant vector of that, as you would expect, we could just use the Pythagorean theorem. Okay? If this is 5 kilometers up, then we can say that this is 5 kilometers up. So what we have left over is this cute little right triangle with a side of 5 and 2. We could find the hypotenuse. So the hypotenuse of the resultant vector should be 5 squared plus 2 squared, whatever that turns out to be the square root of that thing. So the square root of, help me out there, 25 plus 4, sounds like the square root of 29 would work. How would we find the angle? Well, if this one's due north and this one's due east, the angle is going to come from knowing a little bit about trig. And we know that the trig of this angle, or the tangent of this angle, is opposite, which is 5, over adjacent, which is 2. So we would use an inverse trig function, the inverse tangent of 5 over 2, and we're good to go. Whatever your calculator would tell you that. I'll leave you that opportunity to do that. Okay. What happens if they're not at right angles? So let's say we have some goofy vector that's this way, vector B, and then we have vector C coming down in here. Let's just geometrically look at the solution to this thing. And to do that, I'm actually going to, let's see here, we'll ungroup these, and then I'm going to group that together. Okay, so if this is my vector C, I can take vector C, and I'm going to make a parallelogram out of it. This is called the parallelogram method. I'm going to slide this vector over there. If I take vector B, I'm going to slide that down there, and if you'll notice I made a nice parallelogram. Really, this is vector B. This is the exact same thing. It's vector B. This is vector C. This is also vector C. The resultant vector, the one we're looking for, turns out to be the diagonal of that. So this would actually represent vector B plus vector C. We'll talk about the triangle method in class a little bit. It works kind of the same, but we're going to go ahead and do that in class. So see a couple of those. All right, what about this thing called components? Every vector tells you direction and magnitude. Well, if this is your vector and it's at a goofy angle, so I said you have a 100-pound force at 40 degrees above the x-axis, and I believe I know that's not in your sheet. So this vector, if you hopped on and went up it, you'd be going a little bit to the right as you go up. So we would say that this one vector has a horizontal component, which is going to be the exact same length that it would take to get to the bottom of this, and it has a vertical component. And if you think about it, we really just made a parallelogram. It just happens to be a rectangular parallelogram. So we've turned this one vector into its horizontal and vertical. Now if I know this thing is 100, it's kind of like the hypotenuse. All right? And if I know this angle is 40 degrees above the horizontal or the x-axis, now I can use a little bit of trig, because I really want to find the height of this. Well, realize that this and this are the exact same. and realize that this and this are the exact same. So I can use a little bit of trig. I can say, okay, if I want to find the opposite side, which is the vertical component, I could say, well, the sine of 40 degrees equals opposite over 100, because 100 is our hypotenuse. And if I wanted to figure it out, I'd say cross multiply the 100 to the other side, and that should be my opposite. If I wanted to figure out the adjacent side, which is the horizontal component of this vector, I would say cosine of 40 should equal adjacent over 100. And I could cross multiply that 100 over the other side, so I'd get 100 times the cosine of 40, make sure you're in degrees, equals adjacent, and those, I'll let you crank that out on your calculator. Okay, let's wrap this thing up, and then I'm going to give you some problems to look at. Applications of vectors, these turn out to be kind of like story problems, where they'll actually tell you, and I already kind of alluded to one, if you have a freshman and it's getting pulled this way and this way, which direction is it going to go, and they want you to figure that out. Okay? There's a couple good problems on the back of that sheet, which I'm going to show you some solutions to right now. Number 2 on the back, they just want you to set up the two vectors, find the resultant, or sketch the resultant. If you look at the next one on the back, I'd like to set up, they're at different angles. They're at, I think it was a 40 to 70 degree angle between the two of them. Set up what it looks like. The last one I want to look at, you have to break those two vectors into components. The horizontal components are in opposite directions, so you'd subtract them. The vertical components are in the same direction, so you would add those.